Hello everyone. So it's time for meet again. Hope you are well. So today we will continue our class. Before that, we'll be seeing some PowerPoints guided by our audio instruction. After that, there will be few questions in that you have to attend. See, these questions I keep not to test you, just how far you come along with me. That's all. So it is not to put marks and grades. So this is test to the attainment of the knowledge. So go for it, and you can attend only once. So it will be time fixed. So you have to attend and then you come off. And now we will start today's class with a video. Basically, this video I am putting just to understand whatever we see in class. We link our class to day activities. Okay. See the video carefully. How this would have been happen? How this a minor explosion? This is not a major explosion. See, this is direct relevant to our class. How hope one more time you have seen how that has been happen. So let us think over it. How this some may know the answer. So these balloons are not filled with gases. These balloons are filled with hydrogen. Since we see the hydrates and it related to hydrogen, we can also see how this affects our day-to-day activities. Normally in functions like this, we use gas-filled balloons, not air, like hydrogen or helium gas. Suppose if you release it, the balloon, it will go to the top. So this will be a fun for us. Even kids do use it in functions. So a function of this type, we use a large number of balloons which is clustered together and kept. And side by, they have also burned crackers. So you know hydrogen is inflammable, and also the balloon it is touching one over the other. Have you read in physics? If two balloons, if you scratch each other, what does it forms? It forms a static electric charge, which also gives a spark. So that spark would have caused this minor explosion. So students, you understand these things, these balloons have to be separated by keeping a distance. Normally we can say social distance or this we don't have, if you don't want to have an explosion of this type, you have to maintain a distance for balloons or balloons too. So basically, it's a hydrogen-filled balloons, and these would have triggered by a spark of static electric charge. That's what the reason for this. Come, let us go to hydrates. You know that hydrates are the compounds formed with hydrogen. Normally, there will be two things, two elements, out of which one is hydrogen. So last class I described about this hydrates, and we have seen types of hydrates. We have four types of hydrates. Last class we have seen ionic hydrates, covalent, metallic, intermediate, ionic hydrates. All the four types. See the ionic hydrates, which is yellow in color, will be formed with alkali metals. Covalent hydrate will be largely formed with P block elements. Ionic with S block elements. Metallic hydrate with D block elements. And there are some intermediate of having metallic and covalent properties, and those are in this area: copper, zinc, cadmium, mercury. And there are few elements which do not form hydrates, and those we call it as hydride graph, which you may see in white background. Okay, since you have seen hydrate, ionic hydrate with S block elements last class, just we will proceed to the second type of hydrates. So these are last class we have seen ionic hydrates of S block elements. We have also seen the properties, almost around 10 properties, and these are the use they use as a reducing agents. Now we move to the second category of metallic hydrides. So you know the metallic hydrides formed with it will the hydrogen when it joins with D group elements, it forms metallic hydrides. Okay, see D group elements. So I'll start with all we will go from clockwise direction. Start from here, this lower left one. Hydrogen atom being small in size, they occupy in metallic lattice, producing distortion without any change. These hydrates are called interstitial hydrates too. This also I have seen in last class, where in which I have shown a sodium chloride crystal in which hydrogen can be get in. Okay, so here also I'll see in next following slides. In group 6, chromium forms CrH. D group elements 3, 4, 5, 6. That 7, 8 then belongs to hydrate gap. 3, 4, 5, 6, 10, 11, 12 of the F block elements, they form hydrides with hydrogen. And the last we see this 7, 8, 9 do not form hydrides, and that we call it as hydride. Okay. So just you take the element, heat with hydrogen, it forms. Just you take the metal, heat with hydrogen, it forms metallic hydride. Okay. So this is what we call it as interstitial hydrates. Let us see the right part of the slide where there are the metals. These greater the spheres which are greater in size are metals. The blue one, smaller one, are hydrogen, an element or sometimes gases. See, there are larger size of metal atoms inside which we have some space. That space may in which a hydrogen can get in, can peep in, it can get inside. These we call it as interstitial hydrides. Okay. So sometimes an hydrogen or sometimes a hydrogen gas, two hydrogens added together. These we call it as interstitial hydrides. They are hard. Now come to the properties. They are hard, have a metallic luster, they conduct electricity as like the properties of metal and magnetic property. Since there is hydrogen inside these hydrogen in the form of gaseous, their density is little bit lower than the original metals. Then come to third point. These hydrogens sometimes it may be non-stoichiometric. You know stoichiometric in which the proper ratio of two elements. Suppose if you see chromium hydrogen here, CrH, it is one chromium plus one hydrogen. It forms a molecule. But there are something where I have given an example here, titanium hydrogen where 1 is to 73, where titanium is 1, 0.73 is the proportion of hydrogen. Therefore, we call it as non-stoichiometric. You see zirconium hydride. In zirconium hydride, zircon is of 1 part. To 1 part of zirconium, 0.92 part of hydrogen is added. Therefore, this is non-stoichiometric. If you want to ask for an example for stoichiometry, you see the third one. To 1 part of nitrogen, 2 parts of hydrogen is added. This is stoichiometric in full digits, in full numerals. If it is proportion, decimal proportion, then we call it as non-stoichiometric. These non-stoichiometric are quite popular in metallic hydrides. So let us go to the use of metallic hydrides. You know, in many reduction reaction in organic chemistry, we have hydrogen filled with metals, nickel and palladium. So nickel and palladium in which hydrogen is getting absorbed. So those we are used as reducing agents. So you can see here this left part. Due to interstitial hydrogen formation, these metal absorb large volume hydrogen on the surface. This property is called as occlusion. So more hydrogens can be getting inside the metallic surfaces, and that we call it as hydrogen. The amount of the hydrogen occluded depends upon the physical state of the metal, maybe temperature, pressure, etc. And if you heat it, this hydrogen will be liberated, which can be used as a strong reducing agent and also a source of energy. Metals such as nickel, palladium, platinum can absorb large volumes of hydrogen and widely used in catalytic reduction. These are the use of metallic hydrides. Now let us shift our attention to molecular or covalent hydrides. So we move to the third part. We have seen the ionic, the second one is metallic, and third one is the covalent hydrides. These covalent hydrides are largely formed from p block elements. You know the p block is the right part of the periodic table. These are mainly formed from p block elements and some s block elements, primarily due to the electronegative difference between these elements and hydrogen is quite small. If the electronegativity between the element and hydrogen is so high, it will be an ionic hydride. If the difference is so low, then it will be a molecular or covalent hydrides. Okay, let us see the example on right side. Hydrogen fluoride. This is an hydride. Okay, in which we see fluorine, the outermost orbit, the fluorine, it possesses 7 electrons and it is one shot for octet. Hydrogen is 1 electron. Hydrogen is also one shot for doublet. So if hydrogen is having one more, it forms a doublet. If fluorine is having one more, it forms an octet. Those are stable. You know the basics of formation of covalent bond. Okay. So the sharing of electrons takes place here to form the covalent bond. Here you can see the dot is the electron of hydrogen and the cross is the electron of fluorine here. The dot is the electron of fluorine and cross is the electron of hydrogen here. So you can see now the outer shape or the outer shell of fluorine is octet, it is stable, and the outer orbit of the one orbit of hydrogen, it is also doublet, then now it will be stable because of shared electron with fluorine. So now let us see the general formula of covalent hydrogen, and here it has been given XH8 minus N, where X is the element, X is the other element, then hydrogen. So let us understand this formula. XH8 minus N. 8 is the number of electrons present in the outermost shell. Okay. So general, the maximum capacity, where N is the number of electrons present in the valence of any element. In this case, fluorine. So fluorine possesses how many electrons here? You can count. Fluorine possesses 7 electrons here. Okay. Now let us input the 7 in the formula. XH8 minus 7. Because 7 is the number of electrons of present in the fluorine in outermost shell. So 8 minus 7 is equal to 1. XH within bracket 1. That 1 you may put or may not put. It holds good same value. So XH means 1 fluorine and 1 hydrogen atom, which means the formula is this HF. Okay. So the general formula is like this. So you can apply this to any number of elements which belongs to p blocks. And these covalent molecules are held together by van der Waals force of attraction. And now we go to preparation of covalent hydrides. Let us start from this part, lower left one. I will go clockwise direction. By hydrolysis of metal borates or carbides, we may get hydrides. So you know this calcium carbide, if you put in water, you get acetylene gas. This is well known to us in organic chemistry. Even if you go to any shop, this workshop, they use this roadside workshop where they generate acetylene gas for welding purposes. Welding workshop, if you see. So they will take carbide, which is like pellets like. they'll put inside water, acetylene gas will be formed. This gas is burnt to weld metals, to attach two metals together. Okay. So likewise, nitrides and phosphines, if you hydrolyze, you will get the respective hydrides. And this is very easier one where take the direct element, put with hydrogen, upon heating and pressurizing you get the respective hydride. And the third one, so you take chlorides, to that chloride use lithium aluminum hydride, you get the respective hydrides. And the fourth one is by the action of oxo acids with sodium borohydride. So these are the oxo acids. Upon reaction with sodium borohydride, you will get hydrides. The last one by the action of acids. So few elements like aluminum chloride. So if you treat with hydrochloric acid, you will get hydrides. The CH4 is methane. So these are the preparation of covalent hydrates. Let us go for the properties. So let us start from the top left first. Covalent hydrates are usually volatile compound having low melting and boiling point and also do not conduct electricity, which is against metallic hydrates. Metallic hydrates or ionic hydrates, they conduct electricity and heat. The boiling point of hydrates increases as the atomic number or molecular mass increases. Then let us come to the second point. Hydrates of group 13 like boron, aluminium do not have sufficient number of electron, hence they are electron deficient or Lewis acid. So you can see the structure of boron hydride, boron, where to get octet two more electrons are needed. Therefore, this takes electron, this accepts a pair of electron. Hence, these elements we call it as Lewis. Acceptor of electron is Lewis acid. Sometimes, many a times also, borons, silicanes are existing as dimers, trimers, etc. So, in polymeric forms. We'll move to the next third point. Hydrates of group 14 like carbon, silicon, etc. They have exact number of electrons. Let us see the structure you see. The outermost structure is filled with 8 electrons. Therefore, it is not electron deficient, not electron rich. Therefore, it is satisfied. Therefore, it won't act as a Lewis acid or a Lewis base. And the bond length increases from methane to PbH4 as the size of element increases from carbon to lead. Okay. So we'll go to the fourth point. Hydrates of the next higher group like nitrogen, phosphorus and all have more electrons than required. They are electron rich. Since they are electron rich, they may donate the electrons, which call it as Lewis base. Let us see, understand with the structure. You see for nitrogen, it has formed 3 bonds with hydrogen and this electron is excess, which does not involve in any bond formation. Since this does not involved in any bond formation, this may be given us to other species which are electron deficient, may form a coordinate bond. Therefore, these are Lewis base. That's what the fifth point is. What I said now. Just these are used for intermolecular hydrogen bonding, etc. And we also, the last point we also said here, polymer and dimer presence. And again, one more important property what we see is the catenation property. So carbon with hydrogen. It is so catenation property is a property of carbon which joins with another carbon any number of times. So therefore, there is a separate branch of chemistry which reads alone with carbon compounds. So because of this peculiar property or beautiful property where carbon joins with any other carbon in any number. See, it may form straight chain or branch chain or closed chain. So the carbon may form with another carbon in any number of atoms like that. We call it as a catenation property. So this is more in case of carbon in compared to other elements in that group. So, because of this, we study an entire branch of this gives an entire branch of chemistry, which we call it as organic chemistry, due to catenation property. So there are the last part of hydrate, which we call it as intermediate hydrates, where it possesses the property in between metallic and covalent hydrates. So borderline hydrates typically refer to the hydrates formed of hydrogen elements in the periodic table group 11 and group 12. These compounds have properties of between covalent and saline hydrates or ionic hydrates. Okay, the examples, so you can see here CuH and is zinc, mercury, thallium, all those things are intermediate hydrates. So this is about the cu- cuprous hydrate that appears as a spongy reddish brown substance, and it is also a moderate reducing agent. Also, we can form mostly via the acidification or reduction of metallic salts. For example, copper hydride is formed by reacting copper sulfate with hypophosphorus at 70 degrees centigrade and a low precipitate that soon turns red brown. So this is also a preparation. And the another preparation is zinc hydride. We can form with either zinc halide or dimethyl zinc. That is here zinc halide or dimethyl zinc. You heat with sodium hydride, it may result with zinc hydride. So these are the preparation, and it possesses a property in between ionic hydrates and covalent hydrates. So ionic hydrates conducts electricity, whereas covalent hydrates it will be Lewis acid or Lewis basis. So both of the properties will be possessed by these copper, zinc, and thallium hydrates. So with that, I finish the hydrate topic. We complete the hydrate topic. Now I am showing you the pictures of two women. Do you recognize these two women? Well, these two women, they are awarded with Nobel Prize in Chemistry. October is a month where we expect Nobel Prizes across 6 disciplines, and this is for chemistry. This year it goes to two women scientists, and their work let us see. So the 2020 Nobel Prize in Chemistry, it was awarded to Charpentier and Jennifer for the development of CRISPR-Cas9 gene synthesis, a method of genome editing. So let me explain this. See, the expansion of CRISPR, clustered regulatory interspaced short palindromic repeats, that we call it as CRISPR. Okay, so let me little bit explain. Later also you can read by having this slide for some time. Suppose let us take this is the DNA sequence of us. Suppose if a disease affects us, if a virus infects us, already we have immune system within us. That immune, they will fight with the virus which is infecting us. Suppose if that immune system is successful, after that, that system may leaves a trail over our DNA that is like blue in color. So it may leave a trail in our DNA sequence, because this trail it may form a memory like a thing. In future, if the same virus comes again for infection, this will help us in going for again fighting with the second attack. Therefore, this is generally happens in our body systems. These two women scientists, what they taught this as a tool for scissor like a tool to cure any DNA misinformation or DNA deformation in our genes. See, we may get many diseases if a DNA is not in a good man, like Alzheimer's or those kinds of disease. It will come if our DNA is affected. So what they have done is, you see here, it is an infected DNA in the second middle portion. In this infected DNA, they have followed that CRISPR-Cas kind of thing, where Cas is a scissor RNA, and this CRISPR is that which we want to correct it. So what we have to, as like a tailor who stitches our cloth, they will cut it, they will join it. Likewise, the middle part is our infected DNA, and with that Cas19 scissor, they will break it. Our infected portion, they will break it, and the corrected form is here, which we mark is one. That corrected DNA, it will be attached to this RNA, and the malfunction part is thrown over, it is taken away, and it is attached with the newer part, and we will be having an edited DNA. Now we will become all right with our diseases. Now the disease is gone. Okay, this is how it is a tremendous influence in gene correction, so that we will not be worrying about our many diseases. Even some diseases, it will come from generations, from father to the son, from mother to the son, from grandpa to the son. So those diseases can be cured like this, because these comes via genes, and it can be corrected like cas CRISPR Cas scissor like this. So thank you very much for today's class.